ahead. So A4, right, says calculate the pH of an aqueous buffer solution made from 0.15 molar ammonium chloride and 0.1 molar NH3. And then you're given the, the Ka of ammonium. So, right, so this right here is just simply a straight up buffer problem. So what we can use to make our lives a lot easier is the Henderson-Hasselbalch equation, right? And so that equation is just simply pH is equal to pKa plus the log of the concentration of the base, right? And I'll just write that as A minus actually, right? Over the concentration of the acid in that case, right? So you have to have, basically a conjugate acid base pair, of a weak acid, weak base in those cases to, for the Henderson-Hasselbalch to work. So, in this scenario right here, right, we can use the Henderson-Hasselbalch. So we're given, right, ammonium chloride. So that's NH4 plus, right, because that's going to dissociate in solution, right? And then we're also given then NH3, right? And so that's going to be then the base, right? So this right here is HA in this case, and this right here is then going to be A minus in our scenario that we have right here. So, we have those two concentrations, right, that we can plug into our equation. So the other thing that we need to figure out what the pH is, we just need to figure out what the pKa is, right? And so we can get that because we know what the Ka is. We're given that in the problem right here, right? And so the pKa is going to be equal to the negative log of the Ka, right? Let me just, in these cases, right? I mean, that's just like the definition of, pKa, pH, and so forth, right? Those are all simply just the negative logs of whatever the other part of it is. So in this case right here, right, we to calculate the pKa of ammonium, which is the weak acid that we're doing, right, we can just plug in our numbers. So we have the negative log of 5.61 times 10 to the negative 10. And so plug that into our calculator, right? What we get is negative log of 5.61 times 10 to the negative 10. And so what we get in this scenario is a pKa equal to 9.25 in this case, right? So we have the pKa now. We have those two other values. And so to calculate the pH, we can just plug in our values that we have right here. So we have the pKa is 9.25 plus the log of the concentration of A minus, which in this case right here, right, is going to be the NH3, right? The ammonium is going to be the weak base in this scenario. So that's going to be 0.100 molarity over the concentration of the weak acid, right? The weak acid that's part of this buffer. So that's going to be the ammonium chloride concentration. So that's 0.150 molarity, 0.150 molarity in this case. So we take all of that and then we plug that into our calculator. So we have 9.25 plus the log of 0.1 divided by 0.15 gives us a pH of 9.07 in this case right here. So let me just double check, right? That's exactly what I have on the key. So that matches up, right? So, the Henderson, you can go through the whole process of doing the ice table and everything like that. Henderson-Hasselbalch is, if it's a true buffer scenario, right, it's a lot faster, as you can see. It's a lot less messy. And right, for this class, right, Professor Chen's perfectly fine using the Henderson-Hasselbalch. You don't have to go through the whole process of, writing out your ice table or anything like that in those cases. And so that makes it a lot easier. And all you have to do, right, is you just simply, if you know what the concentrations, or even if you don't even know necessarily the concentrations, if you know how many moles of the weak acid and the weak base that you have in that solution, right, how many of those have, right, because all you're doing is looking at a ratio. And because they're in the same solution, right, the molarity is just simply moles over liters. The liters is going to be the same for both of them. And so that's going to cancel out, right? So basically all you're doing is looking at the ratio of the moles that you have in those cases, right? And if you know what the pKa is, you can figure that out from there as well. And you can write, and if you don't know one of the different parts of that equation, right, which is what's going to be happening in the subsequent problems, right, you can kind of rearrange things, right, and you can solve for all of them if you know the other three parts, so to say. So, but yeah, Another thing I want to point out about buffers, right, is that buffers typically only really are stable within, one pH value close to the pKa, and that has to do with the fact that as you start, having more acid or more of the base that's part of the buffer that's present in those cases, right? You start to move further and further away until eventually, you're basically just get converted into it being a complete, all of the weak acid or all of the weak base in those scenarios. But that's how, right? So that's the Henderson-Hasselbalch equation, right? That's just the straightforward way to do it. Oh, another thing that people were very confused by during GPS, right, is that in their minds, right? So in this case right here, right, we're being given a Ka, and there's more of the acid that's present in this scenario, but the pH is still a basic pH, right? It's still 9.07, right? It's not below 7 or anything, and that has to do with the fact, right, that the ammonium, if you look at that Ka value, right, it's times 10 to the negative 10, it's not gonna form a lot of H plus, right, or H3O plus. In those cases, right, the equilibrium favors keeping it as NH4 plus. It doesn't favor it getting converted into H3O plus and H plus, and so you're not going to have that many. You're not going to have that many ions, right? H plus ions in solution, right? Which is what pH is, right? Is just simply a very easy scale of us being able to compare how many H plus ions we have in solution. And so that makes total sense to me, right? That the pH would be that low. Now, right, if you had only ammonium chloride, right, none of the ammonia that was present, right, we weren't in the buffer region or anything like that, right, and that was pretty concentrated, yeah, you'd probably have a lower pH and everything, but you would still have to deal with the fact that it's still not a great acid, right? It's still a weak acid in these scenarios. So that's just one thing to keep in mind, especially when doing these buffer problems, is that they're usually gonna the pH of your buffer is typically going to lie somewhere between like 1 in either direction of the pKa in most cases, right? Because once you start getting outside of that region, things kind of start breaking down in terms of being able to use like the Henderson-Hasselbalch and it being, actually a buffer, because the ratios start to change a lot in those cases. So, but that's A4 with a lot of talking afterwards. So let's keep it moving.